Hello, I'm Gabriele Russo from the University of Rome Tor Vergata, and I'm presenting our work towards quality of service aware function composition scheduling in Apache OpenWhisk, which is a joint work with Alfredo Milani and Valeria Cardellini from Rome Tor Vergata, and Stefano Iannucci from the Mississippi State and Roma Tre universities. The function as a service paradigm is increasingly popular thanks to the scalability it enables, as well as simplified code maintenance and operations and attractive price models. It is currently supported by all the major cloud providers through services such as AWS Lambda and Google Cloud Functions. In addition to this, various open source platforms are available, such as OpenWhisk and OpenWhis. While cloud-based FAS is now an established technology, there are still challenges to be faced to deploy FAS platforms at the edge of the network in edge computing environments. There are multiple reasons to do so. For example, having functions at the edge reduces latency for user-generated requests. Also, some users may prefer running their functions in on-premises servers at the edge for privacy reasons. The key challenges when moving away from the cloud revolve around the limited amount of computational resources available at the edge. For this reason, it becomes more critical to schedule and allocate resources in the best manner. And since it may be the case that not all the requests can be seamlessly served at the edge, platforms should be able to differentiate their service based on the application or the user submitting requests. Research on FAS platforms has been quite intense in the last years, with most of the efforts spent on cold start reduction and mitigation, including the optimization of function startup and initialization, automated function configuration, and better mechanisms for stateful functions, as well as ephemeral storage for functions. There has been also some initial effort to put quality of service at the center of FAS scheduling. For instance, the two works closest to ours are from 2020. For instance, Sequoia proposes a priority-aware and composition-aware scheduling mechanisms for functions. However, they propose a scheduler which is external to the FAS platform and a custom invocation protocol, so their solution is not transparent to existing users. Ensure instead focus on the allocation of CPU time to running functions and present an SLAO-based policy. But their solution does not target compositions. So we envision a quality of service aware FAS platform with first-class support for function composition. The first steps we take in this work comprise the support for additional scheduling policies beyond a simple first-come, first-served approach, adaptive resource allocation to running functions, solutions to mitigate performance degradations under high loads, all to be integrated in a popular open-source FAS framework. As regards the last point, we decided to target Apache OpenWhisk in our work. OpenWhisk is an open-source FAS platform on top of which some commercial solutions have been built, including IBM Cloud Functions. In addition to its popularity, we decided to target OpenWhisk also because it features a per-request scaling system which yields a very similar behavior to what we could observe in cloud-based FAS offerings. Moreover, OpenWhisk supports many different programming languages for function development and supports composition of functions. The OpenWhisk architecture at high level comprises a few key components. Nginx is used as a reverse proxy that receives users' requests. Requests are handled by a controller, which is responsible for scheduling. Actual function execution is performed by invoker nodes, which manage container pools for this purpose. Communication between the controller and the invokers is realized through Kafka message queues. The results of function execution are also sent by the invokers to a CouchDB instance. Now let's see in detail what happens when a function is invoked. Each invocation in OpenWhisk is called an activation. So activations reach the controller after going through Nginx. The controller, having some information about the status of each invoker, tries to schedule the activation to one of them. The controller uses a hash-based algorithm to try to reuse the same invokers for the same function, so as to maximize the probability of worm starts. When an invoker has been selected, the controller communicates to it using Kafka. Eventually, the invoker executes the activation within a container and publishes the result in CouchDB. This is the journey of an activation within OpenWhisk. Actually, the community has been working for months now on a revised scheduling system that aims to improve performance. So if you check the project in the near future, it is likely that something may be slightly different compared to this description. As anticipated, we want to extend the scheduling functionalities of OpenWhisk, especially as regards the supported policies and the management of compositions. So we introduce a new scheduler component in the architecture. The scheduler becomes responsible for scheduling activations to invokers. Furthermore, we equip the scheduler with an internal queue, where activations can wait during overloading periods. Let's see again what happens to an activation in our extended OpenWhisk. Again, new activations reach the controller. However, now the controller just performs basic checks on the request before forwarding it to the scheduler through a dedicated Kafka topic. New activations enter the queue within the scheduler waiting for processing. The scheduler, depending on the policy in use, eventually picks the activation from the queue and selects an invoker for execution. The invoker runs the activation within a container as always. Regarding the scheduler internal queue, the basic idea is having a finite buffer where new activations are enqueued. To manage this queue, a variety of policies can be used, of course. For evaluation, so far we have implemented two well-known policies, that is priority-based FIFO and shortest job first. For the SJF, we let the scheduler collect execution information about functions so as to estimate their service demand. Actually, a limitation we observed in OpenWhisk regards compositions, whose completion depends on the completion of multiple activations. When the cluster is overloaded, OpenWhisk keeps scheduling the first activations of new incoming compositions. However, because of congestion, it takes a lot of time to complete the compositions, and a timeout expires. Therefore, any work done up to that point is lost, and the composition is dropped. To better handle this situation, we introduce a secondary queue within the scheduler, where incoming compositions are enqueued. Furthermore, we impose a limit on the maximum number of compositions that can be concurrently executed at any time. As such, compositions can send their activations to the primary queue only when the current number of running composition is below the limit. We will show that this simple solution significantly improves system behavior. Eventually, activations start executing within containers. Each invoker runs several containers, usually on multiple CPU cores. A natural question is, how should CPU time be allocated to activations? The baseline solution adopted by OpenWhisk, as well as most cloud-based fast platforms, is assigning CPU shares proportionally to the amount of memory configured for the function. Our solution, instead, is to assign CPU time based on the priority level of each activation. For this purpose, we reuse the priority level computed by the scheduling policy within the invoker. We implemented our solution introducing a new component for the scheduler written in Java. The new mechanism required some modification of the controller and the invoker as well. For the adaptive CPU allocation, we resorted to the docker update command, which allows us to change the container configuration at runtime. In particular, we used two CPU-related options, that is, CPU shares and CPUs. The former can be used to set soft limits on the CPU shares available to each container, while the latter can be used to enforce a maximum CPU quota as a hard limit. We also had to revise the Kafka topics used for communication, in order to let components communicate with the scheduler. We also spent some effort to improve Kafka configuration, which has a dramatic impact on the overall system performance, as we will show. Our solution has been published as open source. For evaluation, we compare extended and vanilla OpenWhisk. We use a cluster that is intentionally small to mimic an edge scenario, where the system is easily overloaded. We use two invokers running on 4 core machines, an additional 8 core host for the controller and scheduler. We first deploy 3 functions that respectively generate CPU-intensive, memory-intensive, and I/O-intensive load. For load generation, we used sysbench, a tool for system benchmarking. Then we consider the composition, which is a pipeline for image processing comprising 3 functions. We used relisting invocation traces generated from the Azure Functions public dataset released in 2019. We randomly associate invocations with a priority level out of 3 possible levels. We denote as P1 the lowest priority and as P3 the highest one. Each request is given a 60% probability of being in P1, 30% of being P2, and 10% of being P3. We first verify which is the overhead of our scheduler when using the same first-come, first-served policy used by vanilla OpenWhisk. We consider our extended OpenWhisk version with and without the parameter tuning of Kafka that we performed. As you can see, the extended version introduced some overhead. We found out that such overhead was mainly due to the additional communication going through Kafka, and we managed to make it negligible by properly tuning the message queue configuration. Now we consider an experiment using the priority-based scheduling. The results meet our expectations. As you can see, our scheduler leads to significant response time reduction for P1 and P2 requests compared to vanilla OpenWhisk. Similarly, if we consider our 3 functions which have different service demands and use the shortest job first policy, our scheduler, as expected, improves the response time for the shortest functions, in this case F2 and F3. Besides this, we observe that our scheduler compared to vanilla OpenWhisk leads to a 28% throughput increase in this high load scenario. Then we deploy a function composition and generate requests with different priority levels. Again, the scheduler manages to improve the experience for high priority users. More importantly, we can see the benefits of our 2-level queuing mechanism, looking at the completion percentage of different OpenWhisk configurations. Vanilla OpenWhisk in this experiment completes about 30% of the requests. Our priority-based scheduler, without the composition queue, completes 40% of the requests, but basically drops all the low priority ones. When we limit the number of running compositions using the 2-level queue, we are able to reach a completion percentage of 80%, which is much better than the baseline. A final word on the CPU allocation mechanism we introduced. In this case, unfortunately, the results are not satisfactory for us. The impact of CPU allocation policies on function duration is as expected, so we managed to make high priority activations a bit faster. However, the response time when using these policies gets worse than the baseline, likely because of the overhead incurred when frequently using the docker update command on the containers. So this is currently a limitation of our solution. To conclude, we have presented a new OpenWhis scheduler that supports service differentiation. It has low overhead compared to vanilla OpenWhisk, except for the adaptive CPU allocation as I just mentioned. The main benefit of our scheduler regards the management of compositions under high load, which allows the system to successfully complete many more requests, especially for high priority users. For future work, we plan to introduce new and more complex policies and to reduce the overhead associated with CPU adaptive allocation. Thanks for your attention.